to a lecture series on linear algebra. In this lecture, we are going to talk about linear dependence and linear independence of vectors. Let us get into the lecture. Here, while talking about linear dependence or independence of a vector, we will have to take a collection of vectors from the vector space. Let me take the collection v1, v2 till vn to be some collection in the vector space. Okay, these vectors are to be examined for independence or dependence, right? Let me write down the linear combination of this one, that is alpha 1 v1 plus alpha 2 v2 till alpha n vn. Here you will have to be very careful with the concept that these vectors are taken from the vector space V and the scalars are taken from the field F, right? So here what are we going to do is that we are going to equate this to 0. When is it possible? We know that whenever we give all these things to be 0, we will get 0, right? This is we know for sure. So whenever we choose all the scalars to be 0, we are going to get this to be 0. Okay, let that be. Suppose we have any other possibilities, that is not all alpha is 0. There are few other values which can be substituted and rest of the values are chosen to be 0. In that case also we are getting it to be 0. This may be also the case, right? So we have these two possibilities to get 0. Suppose this is going to be always. So when you have only this possibility, we call this collection of vectors v1, v2, etc. vn to be linearly independent set of vectors. Suppose along with this thing we have this possibility as well, then we call this collection of vectors to be linearly dependent vectors, right? Okay, while saying in a proper definition, how do we say it? A collection of vectors are said to be linearly independent if this linear combination implies all your scalars to be 0. If this is so, we call the set of vectors to be linearly independent. Suppose this implies not all alpha is 0, then we call that to be linearly dependent, right? Let us get into some examples that will make you a clear idea of what linearly independent vectors are and what not. As of now, let me choose the vectors in R2 of R with usual scalar addition and scalar multiplication and vector addition, right? Here let me take my vectors to be 1 0 1 1, right? This is the case I have. Okay, when I write that in a linear combination, what am I going to get? I will get alpha plus beta comma beta. I have this, right? So I have to equate this linear combination to 0 and see what happens. I will have to look for the values of alpha and beta. If these two values have the only possibility that alpha and beta are 0, then this is linearly independent. If not, it is linearly dependent. Okay. So what you have is the vectors are to be equated only if the corresponding entries are equal. Therefore, this is the possibility you have. Beta is clearly 0. This means your alpha must be 0, right? So you can see this is a system of homogeneous equations that you have studied in schoolings. Okay, when you solve a system of linear equations by elimination method, you will always get a trivial solution. System of homogeneous equations. We have 0 here, right? So such type of equations by elimination method will give you only the trivial solution. We have to look for other methods as well, right? Okay, or else I may go with what? I may try to write that in a matrix form. When I write it in a matrix form, I get this thing. Okay, what is the rank of this matrix? Hope you have the idea of the rank of a matrix. right? So when you try and find the rank of this matrix, the rank of the matrix is 2. Here the unknown is also 2. Therefore it has a unique solution. For homogeneous system, the unique solution is the trivial solution. Therefore this is a linearly independent system, right? Let me consider another set of vectors from this set itself. I have this, right? So when I write the linear combination of these things, I get something like this. This is 2 alpha minus 4 beta, 3 alpha minus 6 beta is to be equated to 0, 0. When I write this in a matrix form, what I will get? I will get 2 minus 4, 3 minus 6, right? So what is going to be the rank? Or you just find the determinant. Okay, here we are by determinant also we can find the rank, right? When I find the determinant of this matrix, I will get minus 12 plus 12, which is to be 0. Determinant is 0. Therefore the rank is not going to be 2. Okay, it is less than 2. It is enough for us, right? So the rank is not going to be 2. Therefore it cannot be, these vectors cannot be linearly independent. So they are linearly dependent, right? Which means for different what can I say? Here you can see that this has some relation with this. Okay, 2 alpha is just a minute. My 2 alpha is 4 beta and 3 alpha is 6 beta. Both this implies what? Alpha is 2 beta. So whatever may be the value of beta, you can get 2 beta to be your alpha value, right? So beta can take any values in R, which means alpha is also getting several values in R. So for many values of alpha and beta you are getting, this is satisfied. Therefore this cannot be linearly independent. Therefore they are linearly dependent. Okay. Let us see some more results and problems now on linear dependence and independence itself. Suppose okay, I had now let me take in R3 of R. Okay, let me take this one, this is my set S1. Okay, let me take S2 to be the set, the same set, along with I am taking the 0 vector, right? For simplicity purpose I am taking the values 1 and 0 itself, right? I have these three things, right? So when I try to write this, okay, alpha times of 1, 0, 0, if you are familiar with the notation x, y and z for equations, you can have that too, because there is no harm in choosing the notation, right? So let me choose x comma 1, 0, 0 plus y 1, 1, 1, which is to be equated to 0, 0, 0, right? So what am I going to get is x plus y comma y, which is to be equated to 0, 0, 0. If we write that in you may go that way, or you can see that here this clearly tells you your y is 0. If your y is 0, then your x has to be 0. That is the only possibility you have here. Therefore it is the linearly independent set. Okay, next let me come here. Okay, here x times of 1, 0, 0 plus y times of 1, 1, 1 plus z times of 0, 0, 0. It is to be equated to 0, 0, 0. What am I going to get? X plus y comma y is to be equated to 0. So this also is going to give you your x is 0 and y is 0. But you don't have any restriction for z. Whatever may be the value that you choose for z, you will get this condition is satisfied. Just because you are getting x and y values are 0, you cannot come to the conclusion that it is linearly independent, because if I choose z to be 1, what am I getting? I am getting the scalars in this form. Sorry, I have chosen 1, right? So in this case I am getting it to be 0 0 0, but not all the scalars that I have chosen are 0. It may be 2, it may be 4, 5, minus 7, minus 9 upon 5. Even it is 0. 0 is one of the possibility, not one and only the possibility. The one and only the possibilities has to be 0 for all the scalars that we choose. If that is so, then the vectors are linearly independent. Here it is not so. Therefore what? We are getting linear dependence. From this we can remark one thing. Because when we don't have the 0 0 0, it was linearly independent. Any set consisting of 0 vector is linearly dependent, because this always gives you 0. So the value that you choose with this 0 vector does not matter at all. Therefore this will have infinite number of possibilities, hence results in a linear dependence. Right? Okay. Now let me come to the third one. Here x times of 1 0 0 plus y times of 1 1 1 plus z times of 1 1 0, which is to be equated to 0 0 0. When we do the addition, I have this and then y plus z. Just a minute. Let me write z in this form so you don't get confused with the notations. X plus y plus z, and you have y, right? So 0 0 0. When I try to write that in a matrix form, let me explain this with the help of a matrix. So it is going to be 1 1 1, right? 0 1 1 and 0 1 0. Right? This is the matrix that I have. What is the rank of this matrix? It is easy to find out the determinants for this matrix, right? So the determinant of A is going to be 1 times of 0 minus 1 and minus 1 times of 0 plus 1 times of 0. It is going to be minus 1, which is non-zero. Your determinant is you are getting your determinant to be non-zero. Therefore, your matrix A has the rank same as that of the order of a matrix, that is 3. So when your rank is 3, your vectors are linearly independent. Whenever you have the rank to be the same as the order of a matrix, then your given set of vectors are linearly independent, right? Let me take one more example. Okay, let me choose S4 to be 7 9 12. Okay, this is my set. I will have to check now. Okay, so this is simply alpha times of 9 7 9 12 to be 0 0 0. So it is what? 7 alpha has to be 0, 9 alpha has to be 0, 12 alpha has to be 0. This is possible only if alpha is 0, right? So in this case, my scalar is always 0. Here what you can remark, a set consisting of only one element is always linearly independent, right? So let us pass the concepts of linear dependence and independence as of now for this video, and let us continue with the same ideas in the next video as well. If you have any queries in this video, you can post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.